So I said earlier, it is limited. And here is the scope of the approach. And I think it's worthwhile reminding you of this, ladies and gentlemen, because some of the softwares that people commonly use these days, well, they don't really have any limitations at all. As long as you can model it, then the software will generally report a connection stiffness for you. It's not using the numerical method that you find in 1993-18. It's looking at the deformation, I think, the strains in the joints, and then effectively back calculating what the joint stiffness is. Okay, so these are limitations that you find in the Eurocode. They're not limitations of the generally widely available software. That itself causes some interesting questions, of course, because if you're using the software to compare and contrast with a joint that you have perhaps used the manual method in 1993-18 to look at, then you're very limited in the number of comparisons that you can make. So back in 2020, my good friend and colleague Richard Henderson had a go at using the manual method to calculate joint stiffness. And I would commend you to have a look at his article. So there it is, New Steel Construction, February 2020. And he's going to have a go at calculating joint stiffness. And one of the conclusions is really, as I said before, you only want to do this once in your life. You don't want to do it very many times. You could say, well, it's ideal to do in a spreadsheet. My bitter experience is it would only be straightforward if you've got perhaps only one or two rows of bolts. If you're going to get into a moment resisting connection which has got multiple rows of bolts, then it's going to become very complicated indeed. If you've got things like extended end plates, then you've got lots of effectively if statements, if it's extended or if it's not extended, and so on and so forth. It just becomes very, very complicated. Nevertheless, I commend you to have a look at this particular article. One of the features of this particular article is that it took a joint which had already been designed, and we already knew the strength or the moment resistance of this particular joint. So a lot of the work had already been done. So the first part of the process is to calculate the moment resistance of the joint, which, if you're doing it by hand, is no small task. I will talk about one or two of the features later on, but certainly it's not to be undertaken without a degree of thought. You do need, if you are doing this by hand, you do need to know the lengths of the equivalent T-stubs. That perhaps doesn't mean anything to you at the moment, but it will do in a slide or two's time. All I'm saying is that you need to know some of the intermediate values of certain of the components. So you can't, for example, just take somebody's software and say, well, the moment resistance is X kilonewton meters, job done. Because if you're calculating the stiffness, you need to know some of those intermediate values. The other thing is that you need to know the moment resistance of the joint, because the stiffness, as you'll see on this slide, varies depending on how hard you are working the joint. So we calculate a stiffness, and that calculated value is okay as long as the applied moment is no more than 2/3 of the moment resistance. Now, I think that's interesting because in my previous experience as a connection designer, I wouldn't be over designing the connections by 50%. So the idea that I'd got 50% more resistance than the actually applied moment, well, that would really never have happened. I would be working the connections very hard indeed. So in my experience, I would be applying a moment certainly a lot more than 2/3 of the moment resistance. I might be applying 90% of the moment resistance. Otherwise, I'm just throwing away um, valuable bolts, plate, and weld. So I think this particular aspect of the clause will affect us in the United Kingdom. If we're designing moment resisting connections, we're always working them very hard. I think we would be generally more than 2/3 of the moment resistance, and therefore there is this adjustment factor, which we will see on the next slide. So here it is. The blue line is a typical idealized, I suppose, moment rotation curve. So it goes up initially in a straight line up to the point which is about 2/3 of the moment resistance of the joint. But from then on, it curls over to the right. So if you're applying a higher moment, so I'm highlighting a higher moment now, then you would determine the point that you intersect with that curve, and that would give you, of course, a different stiffness indicated by the diagonal dotted line. So as we get closer and closer to the moment resistance of the joint, then we're going to get a reduction in stiffness. So here's the relationship. It all depends on this value mu, which eventually is going to appear as a denominator. And over on the right-hand side, I prepared a little chart to show you the effect of that reduction factor, mu. So if, for example, we were working our connection at 90% of its moment resistance, then the value of mu is about 0.75. So we're going to find that our joint is not as stiff as we rather hoped it was.